Swayam Prabha. Digital India. Educated India.
Hello and welcome to today's lecture. So, we will as always we will start with briefly recapping what we discussed in last class. We had been mostly discussing about correlation and regression, right. In case of bivariate data, so when you have x and y and you want to see that if you have some trend, can you find out a line, which gives a way of interpolating or extrapolating to determine y at some unknown location. Let us say I can find out, given this particular x star, I want to know what is the value of y star. Okay. So, the way to do it is from the trend itself, we want to find out this equation of the line, right. So, what we do, so in this particular case, when it gives us the impression that there is some linear trend, we fit these data points using a line which is y is equal to a plus bx. Okay. So, clearly this line has equation of line has two unknowns. Okay. These are your two unknowns and you want to find out what is the value of a and b. If you had taken, if your points were 2, if you had only 2 points, then a and b will be uniquely determined. But when you have multiple number of points, then there are infinite solutions to a choice of a and b, and that is what brings us to linear regression. How do we go about finding out the equation of a line which we think is the best representative of this data? Okay. So, one of the strategies which is followed is to minimize. So, if this is the line that I am drawing and these are our points, okay, I minimize the deviation. Okay. I minimize the sum of these deviations from this line. Okay. So, in other words, and I had previously discussed that if these deviations, so deviations are simply y minus a plus bxi. Okay. So, this is you can say ei is equal to yi minus a plus bxi. Now, if you simply do total E as summation ei, this will underestimate the true error, because there are some errors which are positive. So, when y is greater than a plus bxi, so here you have positive error, here you have negative error. So, these will cancel each other, hence this is not the approach to take. So, what you minimize is E is equal to summation of yi minus a plus bxi whole square. Okay. Square means you are minimizing the net deviation without taking into consideration whether it is positive deviation or negative deviation. Okay. And we had briefly discussed that as opposed to a function of a single variable where you take the f prime or the so if you have f of x, so finding out what value this is minimum, you set f prime of x equal to 0. So, when you have g of x comma y, what you do is you set del g del x equal to 0 and del g del y is equal to 0. Okay. So, once again, if gxi is, let us say, equal to x square plus xy plus y square, then del g del x is going to be 2x plus y, because if you are taking the derivative, assume y is constant, plus 0 is equal to 2x plus y. Okay. And del g del y will be is equal to 0 plus x plus 2y, okay, x plus 2y. So, you set both of these equal to 0. So, in our case, the equation is E is equal to summation yi minus a plus bxi whole square, right. So, I will set del E del a is equal to 0 and del E del b is equal to 0, because these are the unknown variables. This is what we want to find out. Okay. So, if I use this particular expression, I can write down 2 So, I essentially take the derivative with respect to this entire term, this is of the form z square. So, when I take a derivative of z square, I get the form of 2z. So, 2 and this is the z, and then of this if I take a derivative with respect to a, so del yi del a is 0, del minus a del a is equal to minus 1, and del bxi del a is 0. So, I get a value of minus 1. So, this equation basically will give you the expression summation yi is equal to summation of a plus bxi. Okay. So, I can write summation yi is equal to summation a plus b summation xi. So, summation yi is basically n times y bar, summation a is n times a, and summation b is n times x bar. So, this gives me the equation y bar is equal to a plus b x bar. Okay. This gives me the equation y bar is equal to a plus b x bar. I can then, so let us do the other expression, del e del b equal to 0 would imply 2 summation, so the first part remains the same. The only thing is now I have to multiply with this, taken a derivative of this with respect to b, which is nothing but minus xi. Okay. So, I can simplify it, I can get rid of 2 and minus. So, I can write it as summation xi yi is equal to summation of a plus b xi into xi. Okay. So, I can simplify it further, is equal to a summation of xi plus b summation of xi square. Okay. So, I can further simplify it, xy is equal to n a x bar plus b summation xi square. Okay. So, I have two equations. So, let me write down the final equations. I have y bar is equal to a plus b x bar, and summation xi yi is equal to n a x bar plus b summation xi square. Okay. So, let us say this is my equation 1, this is my equation 2. I have two equations in two unknowns which are a and b respectively. Now, can I eliminate one? So, I can multiply first equation by n x bar and let us see what we get. Okay. So, I have n x bar y bar is equal to n a x bar plus b n x bar square. So, let us say this is equation 3. So, if I deduct, then 2 minus 3 would imply summation xi yi minus n x bar y bar is equal to b summation xi square minus n x bar square. Okay. So, I can uniquely determine b, the expression for b becomes, so b becomes summation xi yi minus n x bar y bar by summation xi square minus n x bar square. Now, can I compare it with some of the definitions of covariance of correlation coefficient? So, let me write down the expression for covariance that we determined. S x y is equal to summation xi yi minus summation x summation y by n whole divided by n minus 1. Okay. So, you can clearly see, so I can rewrite this equation. So, I can write summation x as n x bar, summation y as n y bar, and by n minus 1. So, I can cancel each other out. So, I simply get xi yi minus n x bar y bar whole divided by n minus 1. Okay. So, in other words, you see that this whole term is nothing but this whole term here. Okay. So, you can clearly get an idea that this is about, so this term is nothing. So, this term is nothing but n minus 1 into sxy. So, if I call it term a, so my a is nothing but n minus 1 into sxy. Okay. So, let us see what is this, so again I will write down the expression for b, this summation xi yi minus n x bar y bar by summation x I square minus n x bar square, right. So, what is this? This is nothing but n minus 1 into s x square. Okay. This is n minus 1 into s x square. Okay. So, I can and this we found was n minus 1 into s x y. Okay. So, my b is nothing but n minus 1 into s x y by n minus 1 into s x square is equal to s x y by s x square. Okay. Now, I know that my correlation coefficient is defined by s x y divided by s x times s y. So, my b can be determined to be rho. So, s x y I can write rho s x s y by s x square. So, then b is nothing but rho into s y by s x. Okay. So, I can determine my b is equal to rho times s y by s x. So, b is the coefficient, the second coefficient I have determined, and I have the other equation y bar is equal to a plus b x bar. So, a is nothing but y bar minus b x bar. Okay. So, I can determine, once I know b, I can determine what is a. Okay. So, let us work out a specific case and see what value we get for x and y. Okay. So, let us take a very simple example. Okay. So, these are our 4 values, or let me make it 5. Okay. 5 is 20. Okay. So, this is my x and y data, and I want to find out y is equal to a plus b x and what are our values a and b respectively. Okay. So, what I need to do? So, as per this equation, b is rho times s y by s x. Okay. So, or I can also write s x square x s y by s x square. Okay. So, I need to find out s x y and s x square respectively. Okay. So, I will write down these values again. So, I have x, I have y, okay, 1, 2, 3, 4, 5, 5, 10, 12, 15, 20. Okay. So, for calculating s x y, I need x y, okay. I also need x square. Okay. So, my x bar is equal to 3, y bar is equal to 25 by 20, 50, 62 by 5 is approximately, so it is exactly 12.4. Okay. Let me calculate x y, it is 5, it is 20, it is 36, it is 60, this is 100. Okay. So, x y becomes 80, 180, 180 or 35. So, summation x y becomes 221. Okay. Let me just cross check again, 180 and 221. Yeah. Okay. X square is 1, 4, 9, 16, 25. So, summation x square is equal to 640 or 53. Okay. So, this is summation x y. So, I can find out the expression for s x y. So, s x y is equal to summation x y minus n x bar y bar by n minus 1 equal to. So, summation x y is 221 minus n is 5, x bar is 3 into y bar is 62 by 5 whole divided by n minus 1 is 4 equal to 221 minus 62 into 3, 186 by 4, 35 by 4. Okay. And s x is equal to square root of, okay. So, S x is equal to square root of summation x square minus n x bar square by n minus 1. So, S x square will be summation x square minus n x bar square by n minus 1. Summation x square we found out was 53 minus n is 5 into 3 square by 4. Okay. So, I can find the value of S x is equal to, so 945, 8 by 4 equal to 2. So, S x is equal to 2, S x y is equal to 35 by 4, my B comes out to be S x y by S x square is equal to, so 35 by 4 into 4, 4 into 4, 16. So, B comes out to be 35 by 16, okay. And A, okay, A comes out to be y bar minus B times x bar is equal to y bar is 62 by 5 minus B is 35 by 16 into x bar is 3. Okay. So, I cannot cancel in anything, 80, 62 into 16, 2, 96, 99. So, 992 minus 525. 467 by 80 is approximately to 46.7 equal to 46 by 7. Let us say we approximate equal to 8 into 46.78. Okay. So, I say A is 5.8 and B. So, A becomes 5.8 and B becomes 35 by 16. 2 is 32, 30, approximately 2.2. Okay. So, your final expression becomes 5.8 plus 2.2 x. Okay. So, if we substitute x is equal to, so we had the value of x is 1. So, x is 1 I see. So, let me again recalculate all our values. Okay. X, y and then predicted. I had 1, 2, 3, 4, 5. My y values are 5, 10, 12, 15, 20. So, my predicted equation is 5.8, 5.8 plus 2.2 into x. Okay. So, what you see here, x equal to 1 is 8, x equal to 5 is 11 is 16.8. Okay. So, what you see here is in the way our points are. So, if you see the percentage of error, okay. So, this raises one important point. If you see the percentage of error, so here you are off by 8 minus 5 by 5 is equal to 60% error. Okay. In here your error is 16.8. So, roughly 20 minus 16.8 by 20 is equal to 3.2 by 20, which is only 6%. Okay. So, this brings us it raises a very important point. When you mark these errors as y increases, okay. So, what you see? So, let us say in a particular case my x varies from 0 to 50. Okay. So, when I and let us say these are my points. Okay. Okay. When I am here, this error is actually insignificant. So, if you count the magnitude of the error, right. So, my error, total error I define as summation E I square. Okay. So, when x is low, when x is small, say let us say x is equal to 1. So, my magnitude of error E1 or E1 is going to be way insignificant compared to let us say E50, that is when x equal to 50. Okay. So, here instead of 3 you are getting a value of let us say 5 or 6. So, your error is 2 or 3, but instead of 50 you are getting a value of 60 or 70, right. So, that error, the proportion of error is, so this is 10, let us say this is off by 10, but this off by 10 has a much significant contribution. So, when you write your error expression, so E50 square is going to be significantly greater than E1 square. So, this would tell you that for higher values your estimate is going to be better than for lower values. Okay. So, how do you tackle this problem? One way to tackling this problem is actually, okay, so one way to tackle this problem is, let us say you have x y, x1 y1 x2 y2. Okay. So, you calculate your let us say z is equal to a plus b x. Okay. You define z1 z2 z3 so on and so forth. So, instead of defining your error as simply summation y minus z whole square, okay, you can define it as summation of y minus z normalized to y whole square. So, what this will ensure is it normalizes the magnitudes of the errors as well. So, between 3 it going up to 5 you have a huge amount of error, but when you normalize by 5 by 3 you get a much lesser amount. Similarly, when you go from 50 to 60, right, your actual error is 10, but 10 normalized by 50 will give you a value which is comparable to this value. Okay. So, you here your error is 2 by 3, so this is 67% and here it is 20%. Okay. So, earlier you were comparing this jump 2 with this jump 10. So, in that case your data will be much better fit in lateral portion, because this error is getting a much greater weightage in this expression. Okay. So, this is one way to normalize. So, of course, in this case you cannot do it by hand, but you have to you have to depend on programming to write down the appropriate code. Okay. So, one more thing I wanted to point out. Okay. So, of course, let us say in the best case situation your data has some linear trend and it is easier to fit a linear curve. But in the more generic case, let us just say, which you will see is very, let us say you have x and y which are related as follows. So, I am actually drawing the curve and not the exact points. Your points, you can draw those points on top of each other, but what you see is the curve is not just a linear line. So, if you fit this data with a linear line, if you fit this data with a linear line, so your curve will look something like this. Okay. But this does not capture the essence of the phenomena you are trying to study. So, it is not always beneficial to just use a line to fit your data. So, you take a look at your data and see what information it conveys. So, for example, right, if your data is like this, right, you can clearly see that there is a nonlinear increase in y with x. What kind of a function should you use? One way is to use a polynomial, right. You can choose a polynomial. Now, depending on how fast this curve is rising, you can choose y is equal to f of x square. So, let us say you can have a naught plus a1x plus a2x square, or you have a function of x cubed. So, you can write function of x cubed also. Okay. But the nature of the rise, how fast the rise is, will dictate what kind of a polynomial you will use. Okay. Now, let us take one more example. Okay. So, let us say you are designing a robot which goes from 2 points. So, this is my x y. Okay. So, 2 points, okay, and at each point, okay, it is going in this particular plane from point A to point B at different times, and you want, so you know at this particular point it has a certain velocity here, and at this point it has a velocity in a different direction, right. So, what you, so this is the x y plane, but this is actually A as a function of, so this is let us say a trajectory as a function of time, right. So, this is time axis. Okay. As a function of time you are moving along xy axis. Okay. And so, you are given two pieces of information at time t naught and time t 1, you are given the position and the velocity. Okay. So, it tells you that there are 4 conditions being prescribed. You are given the position and the position. So, if I were to represent this as my r, so I know what is r vector and what is r dot, okay, or r prime, which is equal to dr by dt, which is a vector, which is the direction. Okay. So, what kind of a function can I choose? So, there are 4 unknowns, right. Let us just say for each trajectory, let us say if I were to assume a trajectory as a naught let us say I assume this particular function. Okay. Now, I write them as a naught, a 1, a 2, a 3 because it is vector, right. Your r position stands for x position and y position. Okay. So, but what you see is, so what you are provided at every time is either the x or the x dot, similarly the y or the y dot. So, you have 2 conditions, right. So, from this, depending on the number of variables you can choose. So, in this particular case you can actually find out the exact solution if you know the position and position at 2 different points and the speeds at 2 different points, right. So, I can use x at t 0, x at t 1, x at x prime at t 0 and x prime at t 1 to find out. So, I can put 4 equations, and if you have 4 independent equations in 4 unknowns, you can uniquely determine. Okay. So, that gives you an idea of what kind of function you can use to fit it. So, linear is only one particular case, but in the generic case you need to fit with different kind of functions. Okay. So, that brings our lecture today to a close. We discussed about regression, we worked out some examples of how you would find out regression, and we showed that using one particular example, we showed that the way we calculate the error, which is the square of the deviations, then for low values of x your deviation is small, hence it gets less represented in the overall definition or overall computation of the error. So, in our way of eradicating it is to normalize this error with respect to the value that you are doing. So, then you relatively give equal weightage to each value. With that, I thank you for your attention and I look forward to meeting you again in next class.